All right. Right. So in the last class, we discussed about the main basic idea behind the motors and generator, which we called as rotating machines. And today, let us see some more details on this and which are very important. So under the heading of principles of electromechanical energy, principles of electromechanical energy, principles of electromechanical energy. Right. So in the last session, we were introduced that so we have electrical machines. So I said machines I will represent M by C. So these electrical machines will convert the electrical energy from one form to another form. And this conversion is taking place through the intermediate domain, which is magnetic domain. So here, so we found that two classes of electrical machines. One is generator, another is motor. Another is motor, generator and motor. And we said that the input to the generator is the mechanical type or mechanical domain, whereas the output of this generator is in the electrical nature. So the output is in electrical domain, whereas for motor the input is in electrical domain, the energy is in electrical domain, whereas the output is in mechanical domain. And we stated previously that the corresponding domain parameters. So if it is of mechanical domain, we will talk about the torque and speed. If it is of the electrical domain, we will talk about the voltage and current. In the same way for motor. And here, if we see this energy transformation, like from mechanical domain to electrical domain or electrical domain to mechanical domain by these two machines, which are generator and motor. So is taking place through the intermediate domain, which we call as the field domain or magnetic domain. So let me say this as like, so I will talk this electromechanical energy as EM, electromechanical energy as every time EM means electromechanical energy. So just as a short form, so the electromechanical energy EM, energy, energy conversion, conversion, conversion takes place, takes place, takes place via, via the medium of, via the medium of, via the medium of magnetic field or just simply magnetic domain, or let me say in detail this that via the medium of electric field, electric field, field or a magnetic field, or a magnetic field. Here you should understand clearly. So once you study the field concept, so what is the difference between electric field and magnetic field? So whereas in electric field there will be electric charge particles that when it is separated, so these fields will be created. When electric charge particles are separated like positive charge, negative charge, let us say this is plus Q and minus Q, the charge particles are separated and the field lines will flow from positive to negative in this direction. The field lines will be established, these we call as a electric field. So the energy transformation may take place through either in the electrical field domain or through a magnetic field domain, but majority is through the magnetic field domain, and what we discuss here is also considered as magnetic field domain. We see why it is. And here the magnetic field domain is because of the moving charges, moving charge particles, where the current is the flow variable, which is the flow of charge carriers, so which is the charge. So this magnetic field will take place because of the moving charge, whereas electric field because of the static charges, stationary charges. So the conversion of energy from these two electromagnetic phenomena, so like, so either from mechanical to electrical or electrical to mechanical, so will be either through these domains. And one important point you should understand here is that, so majority of the electrical machines, the energy conversion is taking place through the intermediate domain, which is the magnetic domain. And why it is that, so the large energy conversion is possible in the case of magnetic domain, whereas in the electric field, so the energy conversion levels are very very low. Means if it is of low energy conversion like small motor, so you can go for the electric fields, but so we will be dealing in terms of megawatts and like mega volt ampere ratings, so we should choose the magnetic field domain as the intermediate. Now let us see in these two machines what kind of phenomena will be taking place. So in the last class we discussed something like the Faraday's law concepts. Now let me summarize that points here, that when a current carrying conductor, when a current carrying conductor, when a current carrying conductor moves in a in a or yeah, so when a current carrying conductor moves, or let me say instead of moves, just as like, when a current carrying conductor is placed in a magnetic field, in a magnetic field in a magnetic field. So what happens when a current carrying conductor is placed in a magnetic field? It experiences it experiences a force, mechanical force, a mechanical force. So thereby this mechanical force, let us say F, so thereby this mechanical force, it result to be a torque and acceleration or the speed. That means, so when a current is supplied to a conductor, then it results to be torque and speed. So in which case this kind of action going to be take place is in case of the motors. So let me write, this will be the motoring action. So in case of motor, so this kind of phenomena going to be take place. So wherever you see like a current carrying conductor is placed inside magnetic field, and if that magnetic field is associated with this conductor which is continuously changing, then it experiences a force, thereby a torque and speed is resulting. So clear? So this is in case of the motoring actions. Now let us see the other kind of thing, like when conductor moves when conductor moves when conductor moves in a magnetic field, in a magnetic field in a magnetic field, then what happens when conductor, bare conductor, simple conductor moves in a magnetic field? So what is the result of this? The result is, or let me write here, so as in proper wording. So when in magnetic field, it it experiences, or it induces, it induces it produces or induces voltage in the conductor. So in which case this will be taking place? In case of the generators. So in case of generators, this kind of action will be taking place. So when conductor moves inside a magnetic field, as because conductor is moving, so it try to associate with the change in flux, thereby it experiences or it induces some voltage in the conductor. This is what the Faraday's law, and this is what the Lorentz force principle, that this force developed is equal to Bf is equal to, or this F is equal to BIL, and whereas this induced EMF E or the voltage is equal to BLV. So these just basic expressions you should little analyze clearly. So what are the parameters which are associated with this force and the induced EMF, which is flux, current, length of the conductor, flux, length of the conductor, and velocity at which the conductor is moving, So, or it can also be expressed in terms of coil. If a coil is moving, so coil N into d phi by dt, this is what the induced EMF. It can also be expressed in terms of N into d phi by dt. Clear? Now just try to understand these conversion, that the fact is that most of the conversion uses this magnetic field domain instead of electric field domain, as because energy storage capacity in the magnetic field is very high. So that weak fields or the small energy conversion takes place in the electric field domain, whereas the strong or the large energy conversion takes place through the magnetic field domain. And whereas, so when we considered here, so like here try to see that what are the required things to produce this force or to produce this induced EMF is, the common thing is, what is the common thing? Just try to observe the flux or the flux density, So here, so we should understand this flux or flux density present where the current carrying conductor is placed or the where conductor is moving. That is one thing. Other thing is that this phenomena, that motor and generator action principles, this energy conversion principles is the same for both AC and DC. So let me write that. So the same principles are the same principles. We study what are that principles are of both AC and DC machines. The same principles are of both an AC and DC machines operation. You will not find much difference between the AC and DC. So we will have flux, we will have current, we will have length of the conductor. That same kind of principles will be applicable. And here just let me elaborate little bit this motoring action and the generator action. Then let us move on to the little electromechanical energy conversion principles. So first let me take the motoring action. So this I already discussed orally, but let me put these in proper wording. So as like this. So for motoring action, just I stated what are the things. Force is developed. How much is that force? BIL. So for which what I need? A flux density or the flux. How can I create the flux? So let us take the north and south pole, something like this. Some magnetic structure, this may be a permanent magnet, so north and south, and flux lines will establish from north to south in this direction as like this. This is well known thing, flux lines will flow from north to south. Here this flux per unit area is what? The flux density. Now what else we need? We need a conductor. So where shall we place the conductor? Inside this magnetic field. Let me consider a conductor here, something like this, which is placed inside this magnetic field. And now what else extra we need to incorporate? It must carry a current of I ampere. So let us consider that this conductor is carrying a current of I amperes. So where does it place? What is the length of this conductor? Length of the conductor is L. This length of the conductor is L. So now when this current carrying conductor is placed inside this magnetic field, what happens? What happens? According to Fleming's right hand rule. Fleming's right hand or left hand? Left hand rule for motor, right hand rule for generator. So you should be very careful about this point. Clear? So according to Fleming's left hand rule, now tell me what is the flux direction? So in that direction you put your forefinger. FBI, remember that FBI. First is the thumb represents the force developed on the conductor. So forefinger represents the flux direction and the middle finger represents the current direction. So you put your middle finger along the flux direction and forefinger along the flux direction and middle finger along the current direction. Then see that how your thumb will be. Can somebody point out this? Place your left hand, three fingers 90 degrees to each other, then turn your hand such that the forefinger is along the flux, middle finger is along the current. Then how does thumb points? So the thumb is pointing for my case, so it is in the downward direction. The thumb is pointing in the downward direction. This is what the thumb. What does it represents? The force acting on the conductor. So just let me put these things in the word that when a current flows or a current flowing conductor is placed inside a magnetic field, then a force is developed on each conductor, this conductor, and as this conductor is placed on certain structure, for which let me take this diagram, just a small thing that see here. Yes, these are for illustration purpose. See this is a simple thing. Here, could you see some copper wire kind of thing? So this is what the conductor basically, copper wire, which is made into so coil form. Here also some copper wire, and here also certain copper wire is there. These are the copper wire or conductor. Now, so where does it placed? It placed on certain core. This is what the core. This is the core. Could you see this some kind of steel material? So on top of this, these coils are placed. And apart from that, there is some kind of rod here. This we call as a shaft. Now what happens is that as force is experienced on this conductor, this entire structure going to be rotated inside the machine. So let me show one more figure also here, that this one, and see here what happens is that, so here see the machine structure. So this same machine, this part is arranged over here. Let me highlight that section. The same part is arranged over here as like this. See, this portion is what, this one is arranged over here. This is what we call as a rotor, which rotates inside the machine. See, this is the shaft. On top of that, this entire structure is mounted, and in that structure the two things are there. One is core coil assembly. This is the core, this is the coil. Core coil assembly. Coil. So what the core coil assembly represents? Magnetic circuit. Clear? So right. Now that entire structure is arranged on certain bearings, and this entire structure try to rotate when a force is acting on this conductor. So that rotating arrangement, entire thing we call as a rotor hereafter. So this entire thing let me call as a rotor. So when a force is acting on the conductor, what does it results? Rotor starts rotating. Thereby a torque is produced. And like, let me put these things. Once a force is acting, so let me take next page. So first force is developed. That force act on the rotor, act on conductor, where conductors are placed on the rotor. So then rotor starts rotating, rotor starts rotating, rotating, then thereby a torque and speed omega is taking place. And as this torque and speed is taking place, you will have shaft, some kind of shaft here. You can you see this shaft? If you arrange some external thing to this shaft, that device also going to be rotated, that try to do some mechanical work. So this is what the motor generalized operation. So if this torque and speed will be utilized for some mechanical work, so that may be pumping the water or just extracting the juice from a sugar cane, etc., like that. And this torque is transformed to the shaft of the rotor, which can be utilized for various mechanical purpose. This is the generalized idea in any motor. Clear? Is this clear? Now let us see the generator action. Generator action. So these points only we will be discussing in detail later on. So just I am giving the basic idea of the motor and the basic idea of the generator. That's all. So just I wrote these 2 points here very carefully. Just try to see. When a current carrying conductor is placed where inside magnetic field, that what I did here. So to demonstrate this motoring action. Clear? So now let us see the generator action. Here, in case of the generator, you have to imagine a reverse operation as that motor. So in case of the generator, what happens is that the rotor is driven by is driven by is driven by a prime mover, a prime mover, a prime mover. Hereafter we will be using this word prime mover. What does prime mover is that? Just like you can imagine your fan, a ceiling fan. So what the kind of operation is taking place? You are giving the electrical energy and it is producing the wind. But just think of in reverse as like wind turbine. So wind is flowing, the blades means the blades are experienced by the wind, thereby it is trying to create some torque on the blades, and that fan going to be rotated. How? Because of the wind. That is what the prime mover. Now wind will be the prime mover. So one wind can be the prime mover, one thing. Another thing is that if you put a high pressure water on some fan, what happens? That fan going to be rotated. That must be made proper structure, of course. So you can say the hydro, the water we talk in terms of hydro. So hydro turbine or hydro water itself, which is impinging on a turbine blades, or just I am using different words, just try to understand. So one is wind can be one of the prime mover, hydro, that is water, can be one of the prime mover, and even steam can be one of the prime mover. Steam can be one of the prime mover. What does these do? These try to produce the torque on certain structure. So as like just imagine wind turbine, you might be seen somewhere. So wind is producing certain pressure on the blades, thereby blades are experiencing some torque, and that torque is going to be rotate that entire structure, what we call as a rotor. That entire structure here I had shown you. So this is shaft may be arranged to, let me say, the same thing. That just one second, the let me copy this figure again. Just think of in this direction, think of in this direction as like this. Now this I have one rotor. What I will do is that just make certain arrangements as like this. For this shaft, I will try to arrange certain kind of blades, fan kind of blades. You might be seen in your, let us say, cooler or somewhere as like this. Some kind of blade arrangements and so on. Now I can put just a high pressure wind on these blades in this direction. This wind is coming at very high velocity. What it happens? It try to rotate this entire shaft. Thereby this entire structure going to be rotated. That is one thing. If I'll put a high pressure water on these blades, what is going to be happen? Again same thing. A torque is acting on this shaft. This entire structure going to be rotated. A high steam may be impinged on these blades, again same thing will be happen. So rotor is driven by a prime mover. What is prime mover? Prime mover is any source which try to create the torque and thereby speed. Clear? Right. So now what happens with this is that if we placed this entire structure as like the machine here, that entire structure on certain structure as like this, then so if this structure is placed inside the magnetic field, inside the magnetic field, now try to imagine this statement that when conductor moves inside a magnetic field, what does happens according to Faraday's law? It induces the voltage inside the conductor. That means inside this coil, then there will be induced voltage. So voltage is induced. Voltage is induced. Voltage is induced in in rotor conductor. In rotor conductor. So this is what the voltage or the power supply in the generator when a rotor which is driven by any prime mover is rotating inside the magnetic field. So this entire thing is placed placed inside magnetic field. Then the next consequence is it produces or induces the voltage. So thereby if we connect any, let us say something like this, you have a voltage source. Now this voltage source is connected across any load. Then when a source is connected across any load, what happens? A current is flowing. So this is voltage across this load, and this is what the induced EMF. This induced EMF E is equal to BLV or N into d phi by dt. So these are the basic principle behind the motor and generator. This you should understand and keep in mind throughout this entire 3 units. Clear? Right. Now let us see some more detail which is very important. So which we call as energy balance equation. Energy balance equation. Energy balance equation. Energy balance equation. So if we see the energy conversion either mechanical to electrical or electrical to mechanical, how does it taking place and what are the different terms involved in that discussion? So that all is depending on the energy balance equation. So let us take the first one, motor action. Motor action. In case of motor action, so what are we doing is that we are giving electrical energy as input I'll write I by P. We are giving electrical energy as a input to the motor. Now what, how this energy is going to be transformed is that one thing I know that there will be some mechanical output. So let me say mechanical energy output, mechanical energy output, OP means output. Now, apart from the mechanical energy output, is there any other energies? Is that general thing is that we all take all the practical things, so there will be certain losses. So let me say that losses as energy to electrical losses, energy to electrical losses. Electrical losses means I square r losses. There will be some resistance for the copper wire here, as like this. I am giving power supply to this machine. That means this conductor is carrying a current of I amperes, where the conductor is having a resistance of R. So I square into R is the loss. That is what the energy loss to the electrical, which is I square R loss. That is one thing, one component. One more component is there will be certain energy to the field storage, electrical, or let me say simply energy energy to field, means magnetic field storage in electrical systems, in electrical systems. This point you should understand very clearly as like this. When magnetic field is established, MF means magnetic field. When magnetic field is established, how magnetic field is basically established is that by increasing the current. If I'll increase the current through a conductor, then in that coil, just like imagine as like inductor. So when flux is established, then it stores the energy. So that stored energy for an inductor is equal to half Li square, half Li square. So it doesn't mean that it is a loss, it is the stored energy. So this may be utilized, the part of the energy may be extracted as mechanical energy output. That's why we are dealing these three components in motoring action. That is electrical energy as an input, there will be certain losses, there will be certain stored energy in the magnetic field, and there will be mechanical energy output. So these three terms we frequently deal. So how we get this power, this energy input is from the supply terminals, from the supply mains, supply mains. Once we give the energy, then that will be split into these three categories. One is the loss component, another is storage component, some more thing is the mechanical output. Is this clear? This all what we talk in the motoring action. And there will be in the mechanical side, there will be certain rotational losses, frictional losses, etc. like that. So similarly, let us take up the generator case. In generator case, what kind of the energy terms will be associated? Generating action. In generating action, the reverse thing. What is that? So we have the total mechanical power, total mechanical energy as a input. So how we get this mechanical energy as a input is that from the prime mover. How we get this? From prime mover. And I already told you what is prime mover. Clear? So this energy, that mechanical energy, is going to produce in case of the generator. So the energy is electrical in nature, output energy is electrical energy. This is what the output. Next is there will be as usually losses. So loss component will be there, total energy dissipated, total energy dissipated. So dissipated in the form of various things. So I will discuss those points in detail later on, but just if you want, just think of as again I square R loss. So which will be basically heat loss. And there are certain other things. Just now let us focus only on these terms. So assume that energy loss, and other component is again stored energy, electrical energy. So or the energy stored. So what term I used? Here energy to field storage, again same thing in the electrical system. So see here, there are certain common things, so you should be very careful, right? So this is the energy to field storage in the electrical system. So now the very important aspect of all these terms, like why I am dealing the energy balance equation, is that so energy will be neither created nor destroyed. So according to the law of conservation of energy, so we need to satisfy every time these equations. For the motoring action, the total energy input is equal to mechanical output plus remaining these two terms. Clear? And whereas for the generator, the total mechanical input is equal to electrical output plus the loss assigned, the stored energy in the field. Stored energy in the field. So these things are very, very important. Clear? So now out of this, the common thing is that loss component and this energy stored component. Loss component and energy stored component in this conversion, like electrical to mechanical or mechanical to electrical. So the loss component is not the major concentration for us, but the second part, this one is very, very important for us. So we deal on these, the energy storage in a magnetic field. This is very important term. Once we understand the stored energy in a magnetic field, then all electrical machines will try to extract this stored energy to get the mechanical output or to get the electrical output. That is what the electrical machines. Clear? So electrical machines will try to take away the stored energy in the field in the various forms. It may be in the electrical form or it may be in the mechanical form. So this is what domain? Magnetic domain. So now let us take the terms which deal on this thing. So is that energy stored in a magnetic field, in a magnetic field, in a magnetic field. This subsection is very, very important. Carefully concentrate on this term. So here we are much interested on the stored energy in the magnetic field, for which, so let me take a simple magnetic circuit that previously we might be dealt this circuit several times. Any magnetic circuit consists of core coil assembly. So let me take the coil as like this, and this is what the coil, and let me extend a little bit. Let us consider it has n turns, and let us say this is excited with a voltage of V, and so let me say this is core coil assembly core coil assembly. So what are we doing? So let us consider n turn coil, and which is connected to a source with a voltage of V. What is going to be happen in practically is that, so this winding or coil has a small resistance, and this going to be induced an EMF inside this coil based on the dot polarity, and this is what the Faraday's law basically. So now this can also be equivalently said as like this. This is the, let us say, in our ideal thing. Now I can resolve this into practical thing as like this. So I'll have a source of voltage V, and this coil has its winding resistance. So let me extract that winding resistance, put together over here. That resistance is R, and now let me take this entire coil as ideal one. Now no resistance for this portion, that whatever resistance is there I took out. So as separately R, and this entire induced EMF is E, and let us say the current flowing through this is I. So this core coil assembly, I made the practical equivalent circuit as like this. Practical equivalent circuit as like this. This winding may have small resistance throughout this length. So that entire resistance I just lumped over here, and remaining is ideal portion. Now this does not have any resistance. Now can I apply KVL for this circuit as like this? Voltage V is equal to the current through the resistance is I into R is the voltage across this resistance, and the induced EMF is E. Now can I put this a little bit more, that IR plus E, can I write N into d phi by dt according to Faraday's law, N into d phi by dt. This can also be written sometimes IR plus N can be brought inside this, so N into phi is the total flux linkage, so that can be called as with the symbol psi. So dt. So where psi is equal to the number of turns and flux per turn. So total flux linkage with the coil is N into phi. So this is what the generalized KVL equation what we arrived, that this is the voltage V. Now let us talk about in this this second term. Why? Because this first term represents the loss basically. If I will consider the power expression, let me take the power, instantaneous power is equal to voltage into current, and where the voltage you can take either of the expression, so as like this, either this one or this one. So let me take this simplified expression. So voltage is IR plus d psi by dt into I. So what does it give? So I square into R plus I into or yeah, so I into d psi by dt, d psi by dt. So this is what the power expression. Out of this, so you can try to observe there will be certain loss component and the remaining is flux linkage component. Now if I want the energy, so what we do? So let us consider that if DC voltage is applied, why I am applying DC voltage is that integration is very easy for me. So to this circuit at t is equal to 0 and ends at ends of t seconds, How does it look like? As like this. If this is the time axis, so I am applying at t is equal to 0 instant, so the voltage will be constant here, and how long it will be there is for t durations, for t seconds. So this is what a DC voltage is applied to the circuit from t is equal to 0 and ends at t seconds. This is what the DC voltage, let us say V. Now if this DC voltage is applied, let us see what will be the energy. So energy input, the energy input is equal to, let me use the symbolic representation for the energy as W. W is not the power, energy is equal to work done. So let me write here for your sake. So work done, which we represent hereafter as W. So work done as W. So suffix is I, which represents input. So how can I get the energy? So energy can be obtained from the integration of the power. How much time interval? Over t is equal to 0 to over t is equal to t. For that interval I am applying the voltage. I want to know the energy accumulated in the system for that interval. So I need to integrate that power over that corresponding interval. So if we complete this, so we will get this as integral over t is equal to 0 to t. So substitute the power expression, what we get? I square r into dt plus integral over t is equal to 0 to t. So what we get? So that expression I into d psi by dt, I into d psi by dt into dt. Clear? So this, don't forget, this is the previous power expression term and dt is common. Now here, so you can just change this integration limits by cancelling dt dt. So let me put that expression over here. So as, so this wi is equal to wi is equal to, so you can express these things, or let me say as it is, no issue. So wi, now can I say this as the stored energy stored energy inside the magnetic field in mf, means magnetic field, in magnetic field. So hereafter this we try to represent the input, or just simply stored energy, or let me say these things as little bit like this. Just I am trying to resolve this energy into two components. One is the stored energy, another is the energy lost in R, resistance R, in resistance, plus stored energy in magnetic field. What this first term represents? Energy lost. What about second term represents? Energy stored in the magnetic field. So now the very important thing is that this second term. So this second term is important for us. The loss component is not so important, but the second term is what? The stored energy. The stored energy hereafter we represent with the WF, the energy stored in the magnetic field. So how much is that WF? So integral over, so T is equal to 0 to capital T. So let me write same expression and later let me simplify, d psi by dt whole into dt. Now here you can do two things. One is, if we are applying the voltage, thereby flux is establishing, and if this integration need to be with reference to flux linkage, then if I'll get cancel this dt dt, then I should take its corresponding flux linkage limit, that is psi is equal to 0 to psi is equal to psi suffix t, means for t interval how much flux linkage is associated with the coil, that is what the psi t. So I into d psi, I into d psi, I into d psi, this is what the flux linkage. The same expression can also be expressed in terms of as like this. So can I say, or let me write, or I can also work on this expression, integral over t is equal to 0 to capital T. Can I write I into the same expression which we written back as over here? See this, where is that? Yeah. So this n d phi by dt instead of d psi by dt. So let me take n d phi by dt. So this one as n d phi by dt whole into dt. Now if I want to change the integration limits, then I should take with reference to flux. So let me take that. So integral over flux is equal to 0 to flux is equal to flux at the instant of time t. So with these intervals, so I into n into d phi. So you can say this either in terms of, let me put, what is ni? Ni is the mmf. Do you remember this term? Mmf is ni. So let me write this as, so phi is equal to 0 to phi is equal to phi t. So this is mmf into d phi, mmf into d phi, or simply ni into d phi, it's your wish. So we may use either of these expressions for the stored energy, for the stored energy, for the stored energy. So be careful. These expressions are very, very important. So this is what the WF. So the energy stored in the magnetic field. So these are very important. Clear? So the stored energy is simply integration of the current with respect to flux linkage or integration of the MMF with reference to flux. So try to observe carefully. What I am saying is that integration of the current with reference to flux linkage or integration of MMF with reference to flux. Is this clear? So these two statements you try to observe very carefully. We will be dealing so these two expressions very frequently. Clear? So now let us see that little bit about these things. Just about these expressions I want to explore with the known things. Known things, what are the known things is that previously we had seen this curve. So I let me check how many of you will identify that this is known to you. So let us say this is flux density, this is field intensity, and now let me just put these lines and let me say what are these characteristics. Can somebody tell me what are these characteristics? Is there anyone? Can you hear me?
Yes, sir.
Yeah. So what are these characteristics? Can you tell me? This red line, what does it represents? We discussed this several times. What does it represents? BH curve, is it?
Yes, sir.
So this can also be called as magnetization characteristics. Magnetization curve. What does this magnetization curve represents is that flux density as a function of flux, field intensity as a function of current, as a function of current. Why? Because flux density can be written as flux per unit area, field intensity like Ni by L. So these are function of current and flux. Now if you observe carefully these expressions, first let me take the flux, this one, d phi. So of the MMF, what is MMF is N into I, N into I. So what does it represents is that this energy stored in the magnetic field is equal to the area between magnetization curve. So where magnetization curve represents flux versus current indirectly, flux versus current, and the flux linkage, see here. So can I say this as like this little bit, just this is very important, carefully observe. Let us assume that over a time interval, over a time interval t, over a time interval t from 0 to t, the current is raised to this value. This may be, let us say, I current I1 for my sake. The flux or flux linkage, you can say this axis either of these two, either of these two, flux or flux linkage, it's your wish. So if this flux is raised to phi t or the flux linkage is raised to psi t, try to understand this. Now the area under this characteristics, area under this characteristics with reference to psi, with reference to psi, that is flux linkage, which area it represents? The area under this characteristics, this is what the area which represents basically this integration. So this we call as the stored energy in the field. Stored energy in the field. The area between the magnetization curve and the flux linkage side, towards the flux linkage. What is the flux linkage axis? Y axis. So that area under this curve on the projection of the vertical axis is what the energy stored in the magnetic field. Energy stored in the magnetic field. So it can also be expressed just if we change the limits, these general things, that MMF and the flux, MMF and flux. So as like just changing these things to flux, and you will see the same expression. That means this can be either expressed as flux linkage or flux. That's what is the difference between flux linkage? Flux linkage is number of turns into flux. This is what the flux linkage, and flux alone is per turn flux, that you should remember. This is what the flux linkage, flux linkage. So here you can see one important fact also, that the WF will represents the energy stored in magnetic field, which is equal to area under the magnetization curve and the flux linkage line. Area under the magnetization curve and the flux linkage curve. So here, so this is what the WF, and let us introduce one more term also as like this, WF dash. WF dash. So WF dash represents the co-energy. So this term I will try to explore in the next class. What is the co-energy? Is that the other side which is not shaded here, that is what the WF dash. And this co-energy concept we discuss in the next class. Okay, thank you.